Hello, this is PreCalculus B, Unit 7, Lesson 3. We're talking about continuous and discontinuous functions, and we're going to define that a little more explicitly using using limits. Right? So I've got a piecewise function on the screen. For x less than or equal to -2, f of x equals 1/2 x minus 2. That's a linear function that is determined or graphed in the green line there. For x greater than -2, f of x equals the quantity -x squared plus 2 times the quantity x plus 2 or x minus 2 divided by x minus 2. The purpose of the x minus 2's was, as you may have guessed, is to create a removable discontinuity at x equals 2. You can manifest this in Desmos by clicking on the point in the graph where x equals 2, and notice it does graph a circle there, and it is listed as undefined. If I can get it back here, it has to be just right. Oh, there we go, right there. 2 comma undefined, right? So that is a hole. I'm going to go ahead and copy this screen so we can draw on it. Okay. And we're going to analyze the graph and determine what the precise definition of a continuous function is. Okay. So here we go. The first discontinuity occurs at x equals -2. At x equals -2, here's what happens. This was equivalent, and so that's an open circle here and a closed circle there. Okay, so the limit, what is the limit? The limit as x approaches -2 from the left of this function, from the left. Well, as it approaches from the left, the function value gets closer and closer and closer to -3. So the limit of f of x as x approaches -2 from the left side is -3. Okay, what's the limit as x approaches -2 from the right side of f of x? Okay, as we approach it from the right side, it's getting closer and closer and closer to -2. Okay, so we can clearly see with this stepwise function or interval discontinuity that there is a disagreement between the left-hand limit and the right-hand limit. Okay. All right, so let's look now at what happens here. We put our open circle here. What is the limit as x approaches 2 from the left? As x approaches 2 from the left, we can see that the function value goes to -2. What is the limit as x approaches 2 from the right of f of x? And you can see that in this case, the limit is right. It is the same. It's also -2. So we can say the two-sided limit exists. So the limit as x approaches 2 of f of x is -2. But we already defined this as a discontinuity, not a continuity. So the left and the right-hand limits and the two-sided limit all agree. But the problem here is there is a removable discontinuity in that f of 2 is undefined. Okay, so hopefully we've got a clear picture of what it takes for there to be a discontinuity. Either the left-hand limit and the right-hand limit don't agree with each other, in which case you've got a step discontinuity, or the left-hand limit and the right-hand limit and the two-sided limit agree, but the function is undefined at the point. As a third example, let's take what happens here at x equals 0, where it is obviously continuous. The limit as x approaches 0 of f of x from the left, it approaches 2. The limit as x approaches 0 from the right is 2. And the function value at 0 is 2. So all three are in agreement. The left-hand limit, the right-hand limit, and the function value are in agreement. Okay, so let's write this following definition. A function f of x is continuous if and only if, that's for IFF, if and only if, that means this works both ways, for all A on the domain f of the limit, let's write the limit as x approaches A of f of x from the left equals the limit of f of x as x approaches A from the right equals the function value of f at A, right? Equals L, some constant limit. So if all three are in agreement for all A on the domain, it is a continuous function. Okay. Now there is one exception. Okay, at the endpoints, let's say we want continuity on a defined domain, a defined limited domain of a domain. We'll define them as the defined boundaries A and B. Okay, the limit as x approaches A, actually, now I've already used A, so let's do this. C and D. The limit as x approaches C from the right of f of x agrees with the limit as x approach of f of x as, actually, just the function value f of C equals some limit. Okay, so in other words, at the boundary C, since there's nothing to the left of C, we don't do the left limit, and the limit as x approaches C from the left approaches D from the left of f of x equals f of D equals some limit L. And actually, I'm going to take that some limit off because that can vary. The limit depends on the function value at that point. So let's take that off. Okay, so hopefully that's clear. All three need to be in agreement for every point on the domain except the endpoints. That is, the left-hand limit, the right-hand limit, and the function value have to be in agreement for the function to be continuous at that point. I don't think the lesson got into the endpoints discussion, but that's worth looking at as well.